Hello, hi everyone. Thanks so much for coming to the talk. My name is Joseph Brooks, and I'm here today to tell you a little bit about an interesting phenomenon that many of you probably saw back in 2015, which captured people's imaginations about visual perception and how visual perception, what we think of as something that should just be objective and clear to everyone and the same for everyone, how it can actually differ between people, and there can be individual differences in visual perception. Just briefly, so I'm going to talk about the dress, but I will talk about more than the dress because there's a wider context of visual perception research that you may find interesting, and which we've known for a long time. I'm a vision scientist. That's my job. We've known for a long time that these types of individual differences in perception can happen. And so I'll talk a little bit more widely about vision science and what we know about perceptual ambiguity. Just briefly about me, like I said, my name's Joseph Brooks. I'm a senior lecturer in the School of Psychology. That's where I sit. Like I said, I'm a vision scientist and a cognitive neuroscientist, so I'm interested in how people perceive things, but also the brain activity that underlies that. I'm also lucky enough to serve in the role of the Dean of Research of the Faculty of Natural Sciences, which means I get the great pleasure of overseeing research across the Faculty of Natural Sciences. That includes chemistry and physics, psychology, life sciences, computing and maths, and geography and geology. So I get to engage in lots of interesting conversations and support for colleagues across the entire Faculty of Natural Sciences. So I'd like to pose a question at the beginning of this talk, and that is, do you think human vision is like a passive camera? Now, when I say a passive camera, what I mean is the old-style cameras that had film in them, right? The new cameras do all sorts of things to the images coming in, right? They manipulate them. They do all sorts of active processes on it. But what I'm talking about is a plain old film camera where literally the light was just projected onto the film, nothing happened, right? Or very little happened. Is that how we think visual perception operates in humans? Or, as an alternative, do we bring our past experiences, our assumptions about the world, to bear on interpreting visual input? So my question is visual perception an objective process that has no input from us, or is it a subjective process where we bring something to bear on it? Are we a blank slate, or are we not? Okay. So that's the underpinning question for a lot of this talk, and I'd like you to keep that question in your mind as we go through parts of this talk. Now, I presumably got you to this talk by calling it the dress, and I think many people are interested in that dress phenomenon that I mentioned already. So just a sense of, in this room, and I can't see people online, I know there's some people online, but in this room, how many of you see this dress image as a blue dress with black lace on it? Okay, decent number of people. And how many people see it as a white dress with gold lace? There are a few people that see it that way, maybe 4 or 5. And how many see something else totally? So a few people see something else totally. So this may seem strange that people look at exactly the same image in the same room, see it differently. That's not what we usually experience in life, is that people usually see the same thing when you're sitting in front of the same image. But this picture of the dress caused a lot of controversy when it came out in 2015, and it spread across the internet because of this disagreement that people had. And people like me, vision scientists, immediately wake up because we're really interested in this sort of thing. So vision scientists across the world decided we need to study this immediately. So we set out immediately doing studies, showing this image to thousands and thousands of people and trying to gather what they saw. And the data on this is just data from 2 different studies that were done in 2017 and 2015 with thousands of participants involved, showed basically what's shown in this room. That is, a lot of people perceive the dress as blue and black. There's some number of people that perceive the dress as white and gold. And there's a smaller number of people that perceive it as, for instance, blue and brown. And then there are a relatively small number of people that see something else entirely. Okay, but it's clear that there's a huge amount of variance in what people see within these categories. In any given room that you can ask this, I get data pretty much like we've seen in this room. Okay, that's been replicated across multiple studies now, so we know it's not a fluke, right? But this is something that we can reliably observe in human observers. The exact percentages differ a little bit between studies, and we'll come back to why that may be the case later on, but it's clear that it's a replicable effect in general. The other thing is that it's not people, most of the time when people see a particular interpretation of the stimulus, of the dress, they see it that way forever. This is not something that changes from moment to moment. You may have seen other visual illusions, like, have you seen the duck-rabbit illusion, where you can see it as a duck or a rabbit, or the faces vase, where you can see it as faces or a vase? With those, people generally can see it from moment to moment differently. You can even push yourself to see it one way or the other way. This one doesn't seem to be like that. In some of these studies, they've also asked people across weeks or days. They've asked them in one moment and then asked them weeks later what they see. And what you tend to see is once people see it one way, they tend to see it that way for long periods of time. So these are just some data where it's a special way of plotting it, where on the x-axis here is what they saw in session 1, and the y-axis here is what they saw in session 2. And what you can see is that every time you see something on the diagonal, a big percentage on the diagonal, that means that they saw it the same way in time 1 and time 2, basically. And what you can see is that pretty much all the time, people see it the same way from one moment to the next. Okay? So the dress is not only variable between individuals, but also it is reliable. I think there's a question.
Can I just ask, sorry to be dim, but what's the difference between naive and non-naive?
Ah, yes, sorry. So in the studies, they collected data from people who had seen the dress before and people who had not seen the dress before, because they wanted to have a sense of whether it was something about knowing about it or not. And what they found was that it doesn't really differ much between whether you saw it before or whether you've not seen it before. You pretty much, people do the same thing. Good question. Okay, so what is this dress? What color actually is it? Okay, well, the dress was actually, the picture was actually taken not too far from here. The picture was taken in the Cheshire Oak shopping mall near Chester, so it is kind of a local phenomenon. This was basically taken by someone who was about to buy a dress to go to a wedding. And they sent the picture they took it in the shop in the Cheshire Oaks, and they sent it to one of their relatives saying, what do you think of this black and blue dress? And the relative was like, what are you talking about? This is not a black and blue dress. And it started that way, and it started to spread more widely within their family and then beyond the family as well. And then it really took off once it got to some news media outlets. The dress is actually a blue dress with black lace on it. You used to be able to buy it on the Roman Originals website. I did try to buy one, but it's out of stock now. So this is, interestingly, some of you may see this as white and gold, but this is the exact same dress, but in different lighting conditions. And I think most of you will probably see these two pictures as black and blue, is that right? Yeah. So there's little ambiguity in these other pictures of the same dress, but this particular image seems to be ambiguous to people. Why? Why is this perception of this image varying between different people? Okay, that's the main point of my talk. Why would this be the case? Well, it really lies in how we perceive things. How do we get visual information into our senses? Well, the way we see things is that light shines on things from various types of sources. Here I've put an image of the sun, but this could be the lights in this room. It could be any lighting source that you have, right, wherever you are. Light shines on objects. Some objects emit light, like computer monitors, but most objects we get reflective light from, but light's bouncing off of them, right? That light bounces off and into our eyes, and that's how we get the information about what's out there in the world. So the light that we get to our eyes is a combination of two things, okay? The technical terms are, it's the combination of what's called the illuminance. This is the brightness and the color of the light that's shining on things, okay? And The other thing that contributes to what the light that goes into our eyes is something called, what's technically called the surface reflectance of something. That's what you would probably call the color of something, the color of paint or the color of ink or dye or whatever. That's what you would call that. So the key thing here is that what the information that comes into our eyes, the light that comes into our eyes, is a combination of two things. The color of the light shining on things and the color of the things themselves. Okay? Now, what we really care about when we see generally is we care about surface reflectance. We care about the color of things. I want to know, is the fruit ripe? I want to know the color of it, right? I want to know, is that t-shirt a black t-shirt or a gray t-shirt? Those are the things I generally want to know. I don't really care about the lighting in the room generally. I care about objects in the world. That's what I want to know about. But the thing is, the information coming into our eyes is not just that. We don't have direct access to that information because the information we get is combined with the light color and the light brightness that we get. So somehow we have to separate these things out. Just a little example, I like this image because it shows how the illumination on an object can significantly vary what's coming into our eyes. So this is clearly a woman standing in front of a window with really bright sunlight shining on part of her. She's wearing the dress, right? And but part of the dress is in shadow, okay? If I took a light meter, I have a light meter back in my lab here on campus, I could take that, and if I shine that on different parts of this image, the readings that I would get from this section of the image are hugely different than the readings I would get from this part of the image. But it's the same object, right? So that light meter, even though I'm measuring the light, doesn't tell me the true color of the object. It tells me something about the illuminance on the object and the color of the object. How do I separate these things out? Okay, that's what I need to do generally when I'm perceiving the world. This isn't unique to these, the reason I show this image is this isn't unique to images like the dress. This is happening every day. We do this constantly. We walk through rooms that have all sorts of different lighting situations. I can walk from here to outside. The color of my shirt doesn't change, but the lighting on it does change. And what I need to do is I need to perceive it as a constant color through all those different lighting situations. Okay. This ability that we have is called color and brightness constancy, that we maintain a constant perception of lightness and color regardless of the lighting situation that we're in. And it's a really important ability for us to have to perceive things accurately in the world. Now, normally we do that really well, right? You did it pretty well in that last image, I'm sure, right? That was clearly a black and blue dress. You do that throughout your lives day to day. But why is this image of the dress so different? Why can't we all do that the same way here? One thing that's clear to me is that the actual dress picture is quite ambiguous in what's actually illuminating this dress. How many of you think maybe it's the shop lighting that's illuminating the dress? So maybe a few people think maybe it's a light kind of in front of the dress shining down on it or something. How many of you think maybe it's natural lighting from the window behind? Yeah, so some of you think that. A lot of people think that. Okay. How many of you think the lighting is a bit yellowish? Yeah. How many of you think the lighting is maybe a little bit more whitish or bluish? Okay, a decent number of people think that. So a big amount of variation in the room about what people think is actually illuminating this dress image. Well, I bet you can imagine that if you perceive the lighting differently, just based on what I've just said, if you perceive the lighting differently, you will do your calculation about what the lighting is very differently, right? So I said your color constancy mechanism is going to allow you to remove the effect of the lighting so that you can get back the colors of the objects. But if we can't agree on what the lighting is in the room, then we may all come to different answers, basically. And it's clear that this image of the dress doesn't have a clear indication of what the lighting is in the room. And that creates a real problem for the visual system, okay? Because the visual system, it can't just say, oh, I don't know, right? It can't just go blank and turn off your vision, right? It needs to give you an answer. It's evolved to always give you an answer, regardless of the fact that the conditions are not great, right? and in this situation, it's got a real problem because it turns out that a black and blue dress under yellowish colored lighting gives you the same exact light to the eye as a yellow and white, more gold and white dress under bluish lighting. So these little connecting bars here are meant to show you that the color is the same, basically, in these two sections, right? If I took a light meter and measured the color there and the color there, I would get exactly the same reading on the light meter. And similarly down here, if I took the light meter and measured there and there, I'd get the exact same reading on the light meter. So we've got real ambiguity here. Depending on which way you perceive the lighting situation, if you perceive yellowish lighting, then you would interpret this as a blue and black dress. Whereas if you perceive bluish lighting, you would perceive this as a white and gold dress. This is the calculation your brain is doing at any given moment. And if you disagree, if you disagree on which illuminant there is, you'll get different answers. Different assumptions about the illumination will give different answers to this question. Okay, just another example of the same sorts of things. So there are at least two possible scenarios from this image for your brain, and your brain has to choose one. Okay. The key thing is that when your brain doesn't know, when there's no good information in that image to tell you which type of lighting it is. Okay, because it wasn't clear from this image I can't see the light source, I can't see much about it. So I have to guess, basically. Your brain can't just say, I don't know, it has to guess. And what it does when it has to guess is it defaults to your illumination assumptions, okay? And those are based on, the fact that we experience a lot of different colors of light across the day. So in any given day, we can perceive more bluish light, which may be in a shadow on a clear day. We may perceive other types of bluish light on hazy days or overcast days, okay? If it's a nice day with direct sun around noon, it's more of a whitish light, okay? If we're inside using somehow more yellowish tinted household bulbs, it's a more orangish light. If we're under candlelight, it may even be a reddish light, okay? We experience all these different types of light. And what we tend to have is somewhere on this scale, our visual system has an illumination assumption, the one that we experience the most, okay? If you live at home and you're mostly in household bulbs with a yellowish tint to it, and that's what you're used to most of the time, then your brain will say, well, if I can't tell from the image, I'll just go with what I usually know, which is I'll assume that the lighting was a sort of yellowish version. And then it will make the inference. Then at that point, oh, the light was yellowish, must have been a black and blue dress, okay? Alternatively, if you're usually in, maybe you have fluorescent lights or very bright whitish lights, it will make that assumption and make the calculation from that, okay? Basically, it seems that we have these illumination assumptions, and these can influence the way that we perceive images when there's ambiguity in the images about the lighting situation. So, this is, anytime vision scientists see something like this is what we assume is happening. So we immediately set out to test in some ways whether this is the case or not. So the way we do that is we take the dress, we cut it out, and we put it on all sorts of different backgrounds, and we play around with it a little bit. So there was one study done by La Sousa in 2015, immediately after this image started circulating, where they cut out the dress and they put it on different types of images. They said, let's put it on an image that looks like everything is blue tinted in that image, basically. It looks like this is a room that's illuminated by bluish light, okay? In that case, almost everyone should perceive that room as illuminated by bluish light. They should make the blue light assumption, right? And then they should see the dress according to that. In that case, they'll see it one particular way. I think that will be the white and gold perception. Okay. In the other example, they cut it out and put it on a yellowish background, and now that should drive people to see this like it's in yellowish light, and they should perceive the same exact image differently. So they should be more likely to see this as a black and blue dress versus that one. And that's exactly what they found, was basically that they could manipulate people's perceptions of the image depending on the type of background that they put there for people. So you can move people's perception around if you change if you give them information about what the lighting in the room may be. Okay. So it's clear, I think, that something about illumination assumptions is happening in the dress. Most vision scientists agree about that. But there's still an open question. Why do individual people have different illumination assumptions, right? Why do some people assume that the illumination is yellow and other people assume it's blue? We still haven't explained that, right? Well, the answer is we don't completely know, but we have some ideas. And one of the ideas is that it's based on your lighting exposure, okay? What you're exposed to in your daily life around lighting, okay? And the idea is that's hard to measure, though. Unless I put a little light sensor on your head and send it around with you for a few months, I don't really know what your typical lighting exposure is, right? That's a really difficult longitudinal study to do. So what we do is we try to use proxies for what lighting exposure you may have. And one way of doing that is a study that looked at people that were more morning larks versus people that were more night owls, okay? So people that are up early in the morning typically are exposed to a lot more bluish light because they're out experiencing natural light in the daytime. So the typical lighting that they're getting is that type of light. It's not as much yellowish, okay? On average. It's not perfect, right? But as a proxy, it's roughly true, okay? And people that are night owls tend to be in artificial light. They're more indoors, which tends to be yellowish, right? Not always, but a lot of the time. So they should actually have a lot more of this yellowish light, and their assumption should be that in any situation where it's unclear, assume yellow light, right? So the key hypothesis here is that there should be a difference in the way people perceive the dress between morning larks and night owls, okay? And it turns out that that is true. I won't go through the data in detail here, but there's been several studies showing that this type of association holds up. If you are more of a night owl, you perceive the dress in one way. If you're more of a morning lark, you perceive the dress in the other way, okay? I still want to do the study where you put little cameras and things on people's heads, but that's quite intrusive. But maybe one day I'll get to do that. So the idea is that, if we use circadian rhythms, people's circadian rhythms as a proxy, we can get some idea about illumination assumptions. Okay, so I just want to say that, so that's kind of what we think, that's one hypothesis of why we think people perceive the dress differently. It's all linked to your lighting assumptions, and then how you use those lighting assumptions to disambiguate images where we don't know what the lighting is. But there are lots of other interesting ambiguities in visual perception. And some of them are linked to lightness and color. How many of you have seen either of these images before? No? Okay. You see that, great. In this image here, there are two squares, square A and B, two labeled squares. If I took a light meter and measured the light coming out of this one, reflecting off of this one and off of this one, how many of you think they would be the same? No. Well, they are. So if I took a light meter and I measured these two squares, I would get the exact same value. So physically, your eye is getting the same exact information in those two squares. Do they look the same to you? No. For most people, they look different. So most people say this one looks darker and that one looks lighter. But the visual system doesn't see it that way, because what it's doing is it's accounting for the fact that, well, that one's in shadow and that one's in bright light. So I need to make some adjustments because the lighting situation is different for those two squares, and I need to readjust them based on the different lighting conditions. Okay, again, this is an example of your visual system constantly doing this every single day. Here's another one. This one's a bit hard to see here, but many of you will see that as an orange square, I think. And that one's more of a brown square. Well, if you use the light meter, it's exactly the same color. There is no difference between them physically. But because this one's in shadow and this one's in bright light, your visual system is adjusting the color difference because they're in different lighting conditions. Okay? If your brain didn't do this, it would actually be quite bad because you would actually get wrong estimates of colors and lights if it didn't do this adjustment. So it's just important that we understand that visual perception is really this process of using assumptions about lighting constantly to adjust the incoming information to try to recover actually accurate information about the external world, because the raw information we get is not directly translatable into what we need. Oops. Okay. I thought I'd also just briefly go over some other illusions that you might have seen, because they show that all of this assumption work and sort of reading into things is not just happening in color and lightness. How many of you have ever noticed that the moon looks like it's a different size when it's low on the horizon versus when it's high up in the sky? You ever noticed this? Yeah. This is something we call the moon illusion. So it tends to look bigger at the horizon and smaller when it's at its zenith, high in the sky. The moon doesn't actually vary in its size as it moves across the sky. So you can measure it that it's the same as it moves across the sky at night. So it's not something physically that's changing about the moon. It's something about the way we perceive it that's changing as it moves across the sky. So the actual path of the moon looks like this. It's always a constant distance from you, and it's always a constant size. Okay, but the way you perceive things in terms of size depends on how far away they are, right? So a tree that's in the distance is often quite small, right, on your eyeball, but a tree that's right in front of you is quite big on your eyeball, right? And what we do is when we perceive things and we estimate their size, we take their distance into account. We need to estimate their size based on how far away they are from us. So I can't just say, oh, that thing's small on the back of my eyeball when it projects onto the back of my eyeball, thus it's a small thing, because then that tree in the distance would look like a small thing. That wouldn't be useful, right? It's actually a big thing. I want to know that. So I need to estimate its distance from me and then readjust its size depending on how far away it is. Okay? And we know that that happens with size perception. There are lots of examples of that. What happens here is that there are different cues to depth as the moon moves across the sky. When the moon is low on the horizon, it may be overlapping with things. You have the visual perspective of the land moving away from you. You have trees slightly overlapping it. You can tell that it's quite far away, okay? Versus when so it looks like maybe it's this distance from you. Whereas when it's high in the sky, there actually aren't that many cues to how far away it is. In fact, it may look like it's closer to you because it's in front of the stars and other things in the sky. Maybe they're around. And so it actually may look like it's close. So what's happening is as it moves across the sky, we're perceiving it at different distances and readjusting its size based on those different perceptual distances from us. Okay. And I'll give you one last example of, can you pass out some of these things here? I'll give you one last example of how we actively infer things in our perception. How many of you know that we have a blind spot in our vision? Yeah. So if I measure the amount, in the back of your eyeball, there are a bunch of sensor cells back there. The names of them are cones and rods. If I just take a cross-section across one part of your eye, 0 here is the center of your eyeball, right where you're focusing, okay? And as you move to the left and right, that's further out in the visual field from what you perceive at the center. And you can see that the rods here, the cones here are distributed across the whole thing. There are lots of rods in the periphery. This is basically how many thousands of photoreceptors there are at different positions across the retina, okay? What you might notice is there is a point here where there is nothing, okay? There is a point at which the optic nerve exits the back of the eyeball where there are no photoreceptors at all. So there are no sensory cells to pick up any light anywhere, okay? Now, if that's the case, wouldn't you expect to have a hole in your vision that you don't see? Do you have a hole in your vision when you look around? Probably not. Yeah, okay. So your visual system must be doing some sort of filling in. So I'm going to help you find your blind spot just to prove to you it's there. So I've got a little, everyone's got a little piece of paper. I always forget which eye I've set this up for. So I think you need to hold it, close your right eye if you can, or block it out, okay? And then what I want you to do is hold this out in front of you and focus your eye on, hold it at arm's length, focus your eye on the cross, okay, the plus sign, okay, with your right eye closed. And then pull that in closer to you very slowly. Keep your eye focused on that plus sign. And at some point, the pound sign should disappear. For me, it's about this distance. The pound sign's gone now, okay? If I move it back out further, the pound sign comes back. I move it back, pound sign disappears. You have to keep your eye focused on that plus. So if you don't keep your eye focused on that plus, it won't work, okay? Keep your right eye closed and keep your eye focused on that plus and pull it in and out. How many people are getting that? Are you getting it to disappear? Yeah, okay. So when you do that, you've moved that pound sign into your blind spot, into that place where there are no sensory cells, okay? And what your visual system's doing is it's filling it in with all white, right? So it estimates the background and it fills it in with the stuff around it so that you don't perceive this gap in your perception, essentially. So this is clearly an example of an active process where the visual system's actively creating information to fill in the gaps because you don't have that information. Okay. So I'm just going to come back to my question. I'm about to ready to finish off here. I'm going to come back to the question I posed at the beginning, and that is human vision like a passive camera? Well, I hope you can all agree with me now. I think the answer to that is no. I think we are very active perceivers. Our visual system is actively filling in information so that we don't have gaps in perception, because it's not allowed to give you a no answer or nothing answer. It has to give you some answer. And we bring our assumptions, including lighting assumptions, including assumptions about how far away things are from us. We bring all of those assumptions to bear and make inferences on the sensory data that we receive into us. So I just thought, we've been talking about sort of visual oddities a bit, right? Things that seem like they're not that relevant. They're fun, but how are they relevant to the world? I was saying that it's fun, but it's not going to change anything in the world. But understanding how the visual system works like this is actually critically important in lots of domains, because in lots of domains you have to make perceptual decisions that ultimately influence job outcomes, security, medical outcomes. So for instance, in medical image perception, radiologists are constantly looking for small changes in medical images, like this scan of a chest here, to detect cancer or other abnormalities in those images. And the way that we look for those things can affect whether we're likely or not to detect them. The assumptions that we have implicitly in our brains that we have no control over affect how likely we are to detect those blemishes or small changes in the image or not. So medical image perception is a big area of work for perception researchers to see, are there ways in which we can help radiologists and other people involved in reading medical images to better detect abnormalities in the images? Because they're often, you might think that they're obvious, right? They're just big things that stand out, but a lot of the time they're not. They're actually quite subtle things. And it's very clear from a lot of the research that we've done in these areas that new radiologists and novices look at these images very differently than expert radiologists do. And it's the way that people look at these images, the way they search them, that can determine how good they are at perceiving them. Just another example, security screening. I don't know if you can sometimes you can make stuff out of these images. Sometimes it's quite difficult. I don't know how you pack your bag, but mine tends to have tons of stuff overlapping in it. And if you look at an X-ray of that bag, it can be quite hard to decipher what's in it. And actually quite easy to camouflage things that are in it, depending on how you arrange things in those bags. And it's critical that baggage screeners are able to accurately perceive what's in those bags, segment those images properly so they can detect weapons or other types of images, weapons and other types of targets. But also not make too many false alarms, because then that holds up the security screening queue, right? So it's a balance that we need not people pressing the alarm button all the time, but people being accurate at pressing the alarm button when they see something in these images, because otherwise it holds up the security cues. So vision researchers are not only interested in these types of things because they're interesting and fun, but because they have real implications for performance in applied domains. And so that's this is what my lab is interested in here at Kiel. I run the Kiel Brain Electrophysiology and Perception Laboratory. So we study perceptual questions like the ones I've been talking about, But like I said earlier, we're also interested in the brain activity and brain processes that underlie those perceptual processes. So this is an example of me with a participant in our EEG lab, where we put electrodes all over their head and record their brain activity while they look at images and make decisions about images. And so we regularly test people like this. My QR code's cut off here, but I've put a QR code in if anyone's interested in participating in studies. We're always welcoming participants to the lab, so if you're interested in getting your electrodes all over your head, just get in touch, and we'll be happy to have you. So yeah, that's it. I mean, my conclusions are, I think the dress shows us that the visual system needs to separate out lighting conditions from the colors of objects. And this shows that the sensory information that we get is incomplete. It doesn't specify directly what causes it from the world. And we use contextual information and heuristics, guesses sometimes, to fill in the gaps and make an informed guess about what is out there. And understanding how the visual system does this is critical for understanding performance in demanding perceptual tasks, things like medical image perception, security screening, and more. So I hope you found that interesting, and thanks for your attention.